Alright, first question, we're looking for the net work done, and this is a force distance graph. So force times distance, which is what you're doing when you're finding area, gives me my work. So I've got this triangle, and I've got this triangle. Notice they're both 1 unit high and 1 unit wide. One is positive, one is negative, so they both cancel out. So that leaves me with just this one, which is just F times D, which is A. Number 2, so we've got a circular platform. It is rotating counterclockwise. No friction. What will increase the angular speed? So I use this relationship. I want to increase this. I know the angular momentum will be conserved as long as there's no external torque. So all I need to do is decrease I. I is rotational inertia. That is, decreasing it would be bringing my mass in closer. So moving towards the center would decrease rotational inertia, which would increase the speed. 3, we've got coefficient of friction is 0.2, so force of friction is mu Fn, 0.2 times 40, so my friction force is 8 newtons. Now I want to write what my net force is. My net force is F equals ma. If I look, this is my free body diagram, my net force is just 8, so that's my only force. If this is your force of gravity is mass times g, which is mass times 10, which means that my mass must be 4. So then, and now we're just deciding, okay, which way is my acceleration? Well, your acceleration comes from your net force. In this diagram, my net force is pointing to the left, so my acceleration must be left. Now I'm moving to the right, that means velocity to the right, not acceleration left. So we want to test whether the net force is equal to the sum of the individual forces. So individual forces would be gravity and the spring force. So I want to test, is my net force equal to the spring force minus the gravity force? So F net is just ma. Fs, so spring force, is kx minus mg. I know my mass and I know my spring constant, so check, check, check. I also know acceleration due to gravity, so all you would need is acceleration and position, B. So you can see that. Here, I want, so let's think of the things I do know. So I measured the time. That's the only thing I know right now. What else would I need in order to measure mass of block B? So we could do, this would be tension, this is tension and gravity. So MA for block B is just tension, whereas MA for block A is gravity minus tension. So you could substitute this in. I'm not going to actually do it because I don't need to work it out. I just need to know the things that I would need if I wanted to find block B. So all I would need, I know gravity, I would need this, and I would need the acceleration. So you'd need the mass of A, and you would need acceleration. So we can cross off B, because it doesn't have the mass of A. Now, just having mass of A in time does not give me acceleration, so that is not enough. If I had the time and the distance, and it started from rest, then I could use acceleration. And I definitely don't need the radius of the pulley. You only need that before taking into account the rotational inertia. But it's a light pulley, so I'm gonna assume a light small pulley is not going to use up a bunch of torque. And then if you want to know exactly how you would get it, you would do. If you start from rest, if you know the distance it falls and you know the time, you can get acceleration this way. Alright, so we've got a sphere and we've got a block. One obviously is going to slide, one slides without friction, so we're going to use conservation of energy here. So for this guy, we go mgh goes to all 1/2 mv squared. This guy has mgh, same mgh, it's going to 1/2 mv squared, and it has to use some of its energy on rotation. So because it has this extra, this one is going to have less regular kinetic, translational kinetic energy than this one. So because it has less translational, because it has to share its energy instead of spending all of its energy on 1/2 mv squared, then it'll have a slower speed, so it'll take longer. So longer time. So the block takes less time, so we're between these two. because it does not spend any of its energy on rotation. It spends all of its energy on the 1/2 mv squared. All right, power. So power is change in energy over change in time. I'm looking from t equals 0 to t equals 3, so the change in time is the same for each. So now I just need to figure out who has the greater change in energy. So change in energy is just work, which is also Fd. I know that they both have the same force, so now I'm just deciding who has a greater distance. So just think about, if I have a mass m and 2m, I pull them with the exact same force. After 3 seconds, they will not have gone the same distance. This guy will have gone a farther distance. This one will go farther because it has a smaller mass. With the same force will be greater acceleration, so we'll end up going faster. On average, therefore farther. So because it goes farther, it'll have a greater change in energy, and greater change in energy over the same amount of time will mean a greater power for that block. All right, here, collision, so P total conserved. So if your total momentum is conserved, that means these both have the same change in momentum. Change in momentum is m delta v. So then because these have to have the same change in momentum, the one that has a greater mass will just have a smaller change in velocity. Now, I'm not saying it has to have a smaller velocity. I'm saying it has to have a smaller change. If you look at this guy from 3 to 1, see it has a change of velocity of -3. From -1 to 1, this one only has a change of velocity of 2, so it has a smaller change. So block 2 is the greater mass. And not because it had a smaller speed beforehand, right? Because just having a smaller speed doesn't mean a smaller change. It's because my final velocity is closer, right? It did not change as much as the other block did. Has kinetic energy compared, so anytime they stick together, that is an inelastic collision, which means you lose kinetic energy. So we can cross out these two. So this one is saying I lose some of the energy because it's transferred into internal energy. So like when they collide, energy, like either think of like cars crashing, right? There's some like literal deformation of the car that takes up energy. Or because their kinetic energies cancel. So B cannot be correct because kinetic energy cannot cancel out. You can't have a positive, or you can have a positive, you can't have a negative. So positive and negative kinetic energies don't cancel out because energy doesn't have direction, so it's only A. Momentums can cancel out, velocities can cancel out because they have directions, but the energies can't cancel out, they don't have direction. What happens to the center of mass? So there was no external force, so the center of mass should have been constant. So I think it's the only one that says that it's constant. Yep. All right, here we've got a velocity graph, average acceleration. Acceleration is the slope of the velocity graphs and its magnitude. So I don't care if it's positive or negative, just care like steep or not steep. So the least magnitude would be here because this has an acceleration of 0, a slope of 0. So the one that has BC as last is D. So I don't even need to look at the other ones because this one had BC as last. Greatest distance would be the area of the velocity graphs. So obviously AB has a greater area, don't need to calculate. Work was done is negative, so work is change in energy. So if you have a negative change, that means you are losing energy. In this case, when we're talking about the velocity, it's kinetic energy, so I want to lose kinetic energy. And then now we just pick the choice that means losing kinetic energy. You lose kinetic energy when your speed is decreasing. If you have less V, you get less kinetic energy. Acceleration is negative does not necessarily mean losing kinetic. You can have a negative acceleration and be getting faster. For example, section D to E. See how this is a negative slope, but it's actually getting faster in the negative direction. So I want when the speed is actually getting slower, so speed decreasing. All right, we are talking about gravitational force, which is this equation, and the electrostatic force, which is this equation. Now you'll notice they both have the same dependence on R. So if they're moved some distance farther apart, I don't know how many times farther apart, and this changes by a factor of n, when this one changes the same distance, see how because they have the same dependence, it will also change by a factor of n. Now it's tempting to do it'll be 1 over n squared. If I were to change r by a factor of n, yes, absolutely, the force changes by 1 over n squared. So for example, if I said my distance is 3 times greater, you would get 1/9 the force. Here, if I get 3 times greater, you're not going to get 1/9 squared, 1 over 1/9 squared bigger, you're going to get, again, 1/9 smaller. Alright, so they're going to change by the same factor, so this is n. Number 19, so we have, this is going to be a wave problem, standing wave, 1 anti-known forms, which means it looks something like this. Stephanie says hi in the video, right, Steph?
Hi guys.
Okay, now we're going to move it to half the original length. So if all I'm doing is just moving it closer so that now it looks like this. So V equals F wavelength. I haven't changed the mass pulling on it, so it should be the same tension, same velocity, it's the same string. But now I have not twice, I have half the wavelength. So that means that your frequency must have doubled, because double with half would keep the velocity the same. So twice the original frequency. Here, increasing the volume. So volume is the amplitude. Amplitude is how much it is moving. So the maximum displacement absolutely increases. So we can cross off these two. Now it's just deciding does the maximum speed and the maximum displacement and average speed increase. So careful with this here. My wave speed does not increase, but I'm not talking about wave speed. I'm talking about the motion of a point. Does this point now move faster on average? And yes, it does, because if at first it's going like this in one period of time and now it's going farther in that same period of time, then of course it's moving faster. So C as well. Right here, energy dissipated. So I thought power, because power is the rate at which energy is dissipated. So P equals IV. And then this is in parallel with these two combined. So I know this guy gets the most voltage, right? If the battery had a voltage V, this would get the full voltage V. This would only get some of it. So these two would split the voltage between them. Now let's think about I. So the two branches, this has a resistance of 200, this has 400. So this gets all of the current. This would only get half the current because it has twice the resistance. And now of course this gets all of the voltage and all of the current, so 200 is the most, so we can cross off A and B. And then now I just need to decide of these two, they get the same current, but because it has the same current with more resistance, this guy gets more voltage, so therefore we'll have more power. So then 300 is next, which is C. Okay. I want something that has a linear relationship with kinetic energy. So time elapsed, we'll come back to that. Distance, I know distance has a work equals change in energy, which equals FD. So see how your change in kinetic energy can be linear with the distance. So this one works. Speed of the block, the relationship between kinetic energy and 1/2 mv squared. Well, this is not linear. See how this would be a quadratic? So not C. Magnitude of net work done. Well, work is change in kinetic energy. So however much I lose is equal to my work. So this should be linear. Right? The more work that is done, in this case magnitude of negative work done, I would be losing more. So those are my two answers. And the reason why time does not work is similar to this. So because you're like the rate at which trying to think of a better way to explain it. I can't think of a better way to explain it. This gives me like the distance over time. The distance would be a linear relationship because if this velocity per time is not a linear relationship, then the time won't work here. Alright, a 2 kilogram rock is dropped into a lake from a few meters and it reaches terminal velocity, so like it stops slowing down or speeding up, stays that velocity after 5 seconds in the water. And during the final 3 seconds, it moves at a constant speed of 4. This is the select two answers again. So would I be able to find the speed of the rock as it enters the lake? So all I know is that it was dropped a few meters above the surface, so I don't know the speed. I know the acceleration as it falls, but I don't know the distance or the time it fell through, so I don't know how I would get that speed. The distance travels the first 5 seconds of its descent. Well, I don't know what the speed it was at the beginning, and I don't know how much it's deaccelerating, so I'm not sure how I would get that. The acceleration 2 seconds before it reaches the bottom. Well, the last 5 seconds, it's at a constant speed, so the acceleration is 0, so yes, I can get that. Change in potential energy, the last 3, so change in potential would just be mg, change in height. I know the mass, I know the acceleration due to gravity. And the height, well, it says it was going at a constant speed in the last second, so yeah, it's only going 12 meters, so I could do that pretty easily. Alright, here we've got 3 charges, and they collide and separate, which are possible values, so just which are possible. And it's, again, 2 answers, so I can cross off B, because the electrons or protons are not going to split in half to spread out. And then the other rule that I have about charge is that the total amount stays the same, so I'm going to check. This one, 3 and negative 3 cancel out, so my total charge is positive 5. Here, 4, negative 4, 5, this is okay. 5, negative 5, that's negative 3, negative 3, this would be plus 4, that is not possible. And then this, oh yeah, this is 12, 12 minus 7 is 5, so these 2 are possible. Collide and stick together. So for a collision, P is definitely conserved, so delta P for the whole system should absolutely be 0 because momentum is conserved. When they stick together, you are going to lose kinetic energy. That's an inelastic collision, you lose kinetic energy, so delta K should be negative, which means less than 0, so C. Okay, so the tension in the horizontal we're going to call T max. And what could the maximum mass be? So I'm going to need to break up, this is just mg, this is T max, this I'll call F, I don't know what to call it, so F. See how the opposite is sine, so this is F sine, and this would be F cosine. These will, if it's at rest, not breaking, these would all be equal, so F sine equals mg, F cosine equals T max. So if I get cosine by, or move the cosine over, I can replace for F. So this becomes T max sine cosine equals mg. Sine over cosine is just tangent. And then to get mass by itself, you would just divide g over. So, E. We are just seeing which of these is possible to do, to like have this. So I want constant acceleration. I want my velocity to be getting slower and then getting faster. So getting slower, then faster. You see how your velocity went to 0 and then it got faster in the other direction. So faster in the other direction. So I think there's only one scenario here that would get slower and then get faster in the opposite direction. So rolling along the floor and then bouncing off should not be like changing speeds in between. Rolling down one side of a bowl and then up would be getting faster and then slower. No. Going up would get slower and then back down would get faster. Falling and then bouncing would be getting faster and then slower. So C is the only one that works. As we travel around an elliptical orbit, so it looks something like this. As we get closer, what happens? So I like to think of it as the L equals I omega. This is conserved. When you get closer, you have less this and more of this. This is talking about angular momentum. The angular momentum would be conserved, so no. There's a gravitational force, yes, and yes, there's gravitational force. This is talking about energy, so I thought of it as the 1/2 I omega squared. So if this decreases but this increases, your kinetic energy is increasing. Your kinetic energy can only increase if you lost potential, because there's no work being done. So loses potential and gains kinetic, like A. Resonance occurs in a soft drink bottle. Which property of the sound wave remains the same as the fluid as the level decreases? So this is similar to like the water, and you like lower the thing, you get a longer pipe, etc. Speed of the wave should absolutely stay the same because you're still talking about in the same medium, so we can cross off these two. If your equation is v equals f wavelength and you know this is staying the same, oh yeah, sorry, I thought it said decrease for a second. Yeah, I want staying the same. If one of these stays the same, see how the other one would have to, right? You can't have the same speed and the same frequency but a different wavelength. So these two will go together, so that's how I can cross off D. And then, so your only option is only the speed or all three of them. As you change this, you will be getting a longer length, but that does not necessarily mean a longer wavelength. So think about ours was like we fit this wave and then we fit in this wave, etc. So we fit the same wavelength, we just got longer to fit more of those waves in, so that's why it's E. Pendulum has a length L and a mass M, which is true of the linear momentum as it swings from highest to lowest. So from here to here, it's tempting to say your momentum is conserved. I actually do have a net force on it. An external force would be gravity. So my momentum should be, not should be, but it could be changing. So let's think. Momentum is P equals mv. My mass is definitely staying the same. My velocity is not staying the same as I move from here to here. It is getting faster, so your momentum should be increasing. Momentum cannot change to angular momentum, right? mv cannot go to I omega. Those are not equal things. You cannot say that momentum converted to kinetic energy, right? Those are, again, like different things. That's like saying mass converted to time. No, those can't happen. They're separate quantities. Ooh, almost finished multiple choice. All right, work is change in energy or FD. Here, I'm going to use forces because I think it's pretty easy to do forces. So you've got the mg sine, mg cosine, normal, and spring force like this. So I want the work done by the force of gravity as it slides down. So only this component is doing the work as it slides down. So the force would be just the mg sine component, and the distance traveled would be the x. So A. It oscillates about an equilibrium position, x naught. What is the spring constant, k? So I'm going to use forces. Equilibrium means balanced. So at that point, the forces are balanced. So these two are equal to each other. So mg sine is equal to my spring force, kx. So then to get kx off, you just divide x over. So that is E. Alright, here one is dropped, but the other one is thrown downward. So at the same instant, one has an initial velocity of 0 and the other one has an initial velocity. So that's not here. Yes, that's true, that's true, that's true, not here. These ones start with velocity and then the other one doesn't, or sorry, 0 velocity and the other one does. And then the only thing that's different about these is the slopes. They all have the same acceleration, which is gravity. So they should both have the same slope, so then B is your answer. And this one, oh my gosh, I didn't do this beforehand. This one's nasty. Gravitational force, one is made, same steel, 3 times the radius, what happens? Okay, so gravitational force is gmm over r squared. So I need to figure out how many times greater each mass is, and then 3 times the radius. So to find how many times greater the mass is, think about we now are 3 times bigger. And it's the same scale, so it's the same density. Density is m over v. The volume is, it goes like r cubed. It has some constants, pi, etc. But I'm just worried about like the factors things are changing. So if I'm going to multiply the volume up to get what the mass does. So these are the only variables that matter. So if I were to plug in 3, that's times 27. And it's the same density, so then I get 27 times the mass. This becomes 9, so 27 times 27 over 9. So this becomes 3. 3 times 27 is 81, so D. Alright, we've got a disc that is spinning. And while the disc is spinning, there's some friction that exerts a constant torque. So a constant torque means a constant angular acceleration, the same way a constant force is a constant acceleration. I have an initial velocity that is positive. So I know my initial velocity is positive. And it comes to rest at this time. So at this time, the velocity is 0. So when I sketch this, at the very beginning, I have a positive initial velocity, and at t1, my velocity should be 0. And because it has a constant acceleration, this will be a constant slope. So straight. Okay, imagine that's a straight line. The angular acceleration, we know that it's constant. So the acceleration is constant, it should be the same value. And it should be the slope of this, which is negative. So any negative value, as long as it's constant, will work. Magnitude of the frictional force is T naught. Derive an equation for rotational inertia I in terms of those things. So you have a couple torque equations. You've got torque equals RF. You've got torque is I alpha, and you've got change in L equals torque change in time. This one will work. I use this one. This one will not work because you don't have R or F, and these things won't help you get them. So I use this one. So I would just be torque over alpha. Torque is torque naught. This is my given. And I just need to find alpha. But I know omega naught and time, so I'm going to use my omega is omega naught plus alpha t equation. I know the final velocity is 0, so subtract over equals alpha. This is t1, divide the t1 over, so this is my alpha. Substitute in. I is torque naught over negative omega naught over t1. You can simplify. If you simplify, that would be the t1 over omega naught. But I would just leave it like this, because don't spend your time simplifying if you don't need to. Alright, in another experiment, still have an initial velocity, omega naught, but then halfway through the time, they start dripping oil so that we reduce the friction. So I should have less torque from 1/2 T1 to T1. So less torque means less angular acceleration. So it will not so slow at the exact same rate. It will be less rate than before, so reducing the friction. So notice that for the first half, until t equals 1, it was still the same. So I'm still starting at omega naught. Everything's the same to t 1/2 t. And then it's only in the second half that something has changed. So from here, I have less acceleration. So instead of doing, this should be straight by the way, instead of keeping this constant slope, now I have less slope, so it should be kind of, I don't know, dying off like this. So it's still slowing down, right? The friction didn't go away, but I am slowing down at a slower rate because I have less acceleration. Now my angular acceleration, again, everything is the same for the first half, and then they drip oil, and I'm getting less torque, so I should be getting less acceleration. So I have it just decreasing. And it didn't say it went to acceleration of 0. I think you can make it go to 0. You cannot make it go on the other side, because putting enough oil does not make it start accelerating the other way. It's just not slowing down as much. Okay, so we have two equations we can choose from based on which makes sense. So I'm worried about what the torque is doing with t, because t1 is a constant and c's are constant, so I'm not worried about them. So I should think, as t increases, what should what should the torque be doing? So as I spend more and more time, see how you're dripping more and more oil? This is reducing the torque, so less torque. So as time increases, you should be getting less torque. So then now I'm just looking, okay, if I multiply by this, yes, there is subtracting, but I'm looking at time greater, so that'd be multiplying by bigger numbers. I want to divide. So 2, because as time increases, torque should decrease. Right, here we've got a wave on a string, P and Q. It says this is at maximum displacement, this is 0 displacement at equilibrium. I want to draw an arrow of the velocity of the point. So at this point, see how it's between going up and down? This one would have a velocity of 0. At this point, it is not a velocity of 0. If the wave is moving this way, see how the point Q is on its way up? Because a minute ago it was down, not over here, but like it was down. And then as this moves over, it's going to be going up. So velocity of point Q is up. Here now I want the acceleration. So here, this one has an acceleration towards like the equilibrium. And this one is at equilibrium. It has no acceleration at all. All right, this is like literally a snapshot of the wave, which is moving to the right. I want to draw the string at t over 1/4, where t is the period. So I want to do it 1/4 of the period later. So right now I have this wave, right? 1/4 later, see how this would just be shifted 1/4 over. If this is one wave, this is half, this is 1/4. So this would now start here. It would look, I can do this. Yeah, I've just shifted it over 1/4. So I'm going to draw the same thing like this, and then I'll just continue. So this is my wave, and it says, there's something else. Draw a dot to indicate the position of point P at this time, and clearly label it with point P. So point P was right here. Remember, what waves transfer is energy, not matter. So if the wave is moving to the right, point P is not moving to the right. In fact, the oscillation of the points is up and down. So as this moves to the right, P was on its way up. It's still in the same position, like X position. So it was over here, and now that point of the wave is right here, and I need to label this P. There is part C. Consider the wave at T. Time period. What is the distance traveled? Not displacement, because it'll be back where it started in a period, but how many centimeters has it actually moved between this time and this time? So think about point P. In a full cycle, will go up and back down. So it'll go up 8, and down 8 and 8. Up 16, down 16 is 16 plus 16 is 32 centimeters. We've got a block, and at first it's just M on a spring, and now it is 2M on a spring. I want to find the ratio of the period. So period is 2 pi square root of M over K. So period PQ has all the masses, which is 3M, over period P, which is just 1 mass. Obviously, if we're dividing this over this, the 2 pi's cancel out. The dividing by k's cancel out, and the m's will cancel out, but you are left with a root 3, which is your numerical ratio, equals root 3. So here, I didn't want a ratio as like something to something, right? The ratio was this over this. This over this would give me root 3. Right, now I want to know how would the amplitude compare now. So would it be going farther, displacing farther, not as much, or the same as it was before? The key thing here is that this was dropped on while it was moving, at equilibrium, so while it's moving. So I have a collision here. In a collision, we know momentum is conserved.